Good morning, fellow ME 301 classmates. My name is Charles Cradwell. The article I chose was entitled Free Volume Holes Diffusion to Describe Physical Aging in Polymethyl Methacrylate Silica Nanocomposites. Here's some background information about me. I live in Buchanan, New York, a suburb about 1 hour north of New York City. I'm a very happy husband and father. You can see me in the below picture with my wife, my young son and daughter, and to the side our dog. I currently work as an inspector at a nearby county health department. I also work part-time in an environmental laboratory where we mainly test materials for the presence of lead and asbestos. In the bottom right-hand corner of the slide, you can see a picture of me working one night. You're probably asking yourself, what is polymethyl methacrylate, which is often abbreviated as PMMA? Commercially, it goes by a few names. Two of which are plexiglass and lucite. It's a clear polymer used as a shatterproof replacement for glass. It's found in safety goggles and glasses, in the glass screen that goes around a hockey rink. It's also dissolved in latex paint, lubricating oil, hydraulic fluids, and increasingly it's used in nanocomposites, and it's replacing traditional metals and ceramics used in a variety of applications. In the bottom right of the slide, you can see an aquarium window made out of plexiglass, and on the left you can see a pair of lucite high heels. The researchers proposed and tested a model to explain why the PMMA silica nanocomposites will undergo densification more quickly than their bulk counterparts with no nanoparticles. Densification is another attribute of physical aging. Another third attribute is enthalpy recovery. Generally, physical aging is defined as a return to thermodynamic equilibrium in a liquid after it's cooled below its glass transition temperature. The authors postulated that this was due to free volume hole diffusion in the amorphous polymer matrix. This is similar to vacancy migration described in our textbook in a crystal structure, with the major difference being that I don't believe the PMMA silica nanocomposites are crystalline in structure. The authors do not come out and say this explicitly, but based on my understanding of polymers from the course text, it's unlikely. The text states that crystallization is unlikely due to the lengths of the chains, and when it does occur, it usually occurs in very small portions of the overall mass of the polymer. The hypothesis of the authors goes against the commonly held view in the material science field that the difference in physical aging is caused by molecular mobility. Molecular mobility can be described as self-diffusion, also mentioned in the course text. To accomplish their goals, the researchers solved fixed second law numerically as opposed to analytically, using what they termed a finite code element. Below you can see a general form of fixed second law, which is a second order differential equation. They then took previously obtained experimental data on enthalpy recovery for PMMA silica nanocomposites, and then they had to convert the nanocomposite into its thin film equivalent, because their model was in 2 dimensions. After doing this conversion, they applied a sampling of specimens with a statistically meaningful range of equivalent thicknesses. And in the bottom right, you can see a schematic of what's going on. The large grayish dots are the nanoparticles surrounded by a white interface. The small white circles are the free volume holes, and the background is the polymer matrix. As you can see by the arrows, the free volume holes are diffusing towards the interface. The authors of the study found that in all cases, the data on enthalpy recovery fit their diffusion model in a statistically meaningful manner, leading them to conclude that the free volume hole diffusion model is adequately able to explain the increase in the rate of physical aging between the PMMA nanocomposites and the bulk material, while also accounting for the fact that the molecular mobilities of the nanocomposites versus the bulk material does not change. There's no difference in molecular mobility. However, they do concede that their model does not hold in all theoretically possible cases. But note, it only does not hold in conditions that are experimentally unobtainable, such as if a specimen was to have an infinite rate of cooling from above to below the glass transition temperature. In other words, they're saying that in the hypothetical situation that the specimen was cooled in 0 time, their model would not hold. 2 questions I offer the class are: what type of diffusion in crystal structures most closely approximates the diffusion of free volume holes in the PMMA matrix? That type is vacancy diffusion. My second question is: are polymers generally crystalline in structure? The answer to that question is no. Polymer crystals are very difficult to isolate and unlikely to form crystals due to the lengths of their chains. And when they do, the mass is minimal in comparison to the overall mass of the matrix. Thank you very much and have a good day.